wrong with my video today. So I am not sure what's going on. And yeah, I'm yellow and my camera is not turning on. Can you hear me okay? Okay, well, at least you can hear me. You don't necessarily need to see me. I have no idea why I'm yellow today. Um, so it's very strange. You know, it's something new every day with technology. So anyway, so how's everybody doing? I hope you're doing okay. I know I am looking forward to our week off, our reading week next week. Yay, reading break. I'm sure everybody's looking forward to that. So, all right, so we are going to talk about, well, we have one more topic from chapter 6, actually, that we're going to look at, but then we're going to go on to chapter 7 and a new topic. So this comic here is about our new topic. And I wonder if anyone knows what this comic is about or what it's referring to. Has anyone seen this before or know what it's referring to? You may have learned about this in high school, possibly. Well, what it's referring to, since nobody's jumping right in, it's referring to something called, no, not internet safety. It's referring to something called the Heisenberg uncertainty principle, which is something you might learn in Physics 102. It depends a little bit on which topics they cover. But it's the idea that you can't simultaneously measure both the position and the momentum of an object. And momentum is our topic for today. Oh, you learned it in chem. Okay, good. So, so you can either know the position of an object really well, or you can know its momentum really well, but you can't know both. Okay, that there's an inherent quantum mechanical uncertainty, which is one of these weird quantum mechanical phenomena that we have to deal with when we look at microscopic objects. Okay, so yes, that's one thing I wanted to point out is I am trying an experiment today because the class size has routinely for the last week dropped below 250. We are now in the mode where we can do breakout rooms and you can turn your mics on and stuff, though it's probably good not to turn them on in the middle of class. Okay, so be careful. And you can also turn your cameras on. And so what we're going to do today, we might try some breakout rooms because that's the other feature that we can do now, especially since we have a somewhat smaller group today. Okay. Rasul was sick. Rasul was sick. Okay, and I think he's mostly better now. So hopefully at some point, Rasul will rejoin us. So yeah, so I'll tell Rasul that you guys miss him. So that's very sweet. And the other thing I wanted to point out before we start talking about momentum is that I noticed that the lecture recordings in BB Collaborate are they're going to start disappearing. I think they only get saved for a month. So like, for example, the first day of class has already disappeared. So if there are any lectures you wanted to save, you should try to download them. I've set it up so you can download. I'm going to see if I can put them all on another site somewhere so that you guys can access them for studying later on. So I've started to download them myself, but just to point that out. All right, so what are we going to do first here? Let's find, it's very disconcerting to have that yellow there. Okay, so we're going to switch to the slides now. So you think if I go to calendar, you can, oh, I can change the dates? Anyway, I will look into it. So, so like I said, before we get into talking about momentum, we have one more topic. This is a topic that doesn't show up in the pre-lectures, but it's a pretty important topic. So, so we're going to do it in class. So we're going to talk about power. So what is power? Power is the rate at which energy is transferred or work is done. And it's actually a pretty important concept. So basically, it's not just important how much energy gets transferred or how much work is done, but it's also important how fast it is done. Okay, you probably have heard of power referred to in various different contexts. So the way we calculate power, it's pretty straightforward. In the case of work being done, it's the work divided by the time elapsed. So it's the amount of work done in a certain amount of time. Our work units are joules, our time units are seconds. So power is measured in joules per seconds, and we have a name for that. We call that a watt, which is named after James Watt. He and Joule were scientists in England at about the same time working on steam engines and things like that. So watt is a pretty familiar unit. You've probably seen light bulb packages labeled with watts. Okay, these are LED light bulbs that are meant to look like or be as bright as 100-watt light bulbs, 100-watt incandescent light bulbs, which are the old-fashioned light bulbs we used to use. So 100 watts, not a huge amount of power. There are other devices in our lives that use a lot more power. Here's another example of a device that uses a lot more power. Okay, this is an 1875-watt hair dryer. Okay, quite a bit more power. Okay, quite a bit more electricity energy being used here per second. Luckily, you don't run a hair dryer for very long. So, but anything that heats things up or cools things down tends to use a lot of power. So your refrigerator typically runs about 600, 800 watts. Microwave ovens often are like 1200 watts. So, so that's one thing to be aware of with watts. So let's look at a simple situation. Say we go back to our roller bag. Remember, we were dragging our roller bag across the airport, if we ever get to go back to the airport. And you're pulling with a force F at an angle theta, and your bag undergoes a displacement D, like this. So let's say you're dragging your bag at a constant velocity, okay, that you're not accelerating. That means there must be another force, right? There must be friction, right, opposing the pulling force along the ground, opposing that horizontal component, right? Otherwise, you would be accelerating. So say you're pulling at a constant velocity like this. You can come up with a different expression for the power exerted by the force F, okay? The power would be, again, work over time elapsed. And remember, our work would be our magnitude of the force F, magnitude of displacement D, times the cosine of the angle between those two vectors, divided by the time elapsed. But then we can say, oh, but wait a minute, displacement over time elapsed, that's just velocity. So we can rewrite this. That's the magnitude of the velocity, right? Magnitude of displacement over time elapsed. And so we get a nice expression for when a force is being exerted and the object is moving at a constant velocity, that it's just equal to F cos theta times the magnitude of the velocity. So I thought we would try an example to see how this works. This is another one of our biological examples that was put together by one of my colleagues who's a biophysicist. So we're back to little bacteria. These are motile bacteria like E. coli, which my understanding is that E. coli are not nice bacteria. And they can swim at a constant velocity of about 30 micrometers per second. So we'll see the equation again in a second. Their spinning flagella provide the motive force that balances the viscous drag force that they experience. Remember, they're usually swimming around in a fluid, and so there's a drag force. And the motive force is equal to about 1 piconewton, tiny, tiny, tiny little force. Okay, so first question, how much power is the motive force using while the E. coli is swimming? So here's our spherical bacteria. Again, I don't think E. coli are spherical, okay, and we didn't draw in its flagella here, but here's our little spherical, okay. And so you can see we've got our drag force and we've got our locomotion force, okay, or motive force, as you might call it, FL. And our bacteria is happily moving at a constant velocity, okay, because those two forces are equal and opposite. Okay, so E. coli are nice in symbiosis. That's interesting. Okay, so back here's our formula again for power. Okay, so power again is equal to force times cos theta times the magnitude of the velocity. And in this case, the velocity and the force are in the same direction, so theta is 0, so we get a cosine of 1. So it's just the magnitude of the force times the magnitude of the velocity. Pretty easy to figure out. So we're going to plug in our number. So now a pico, remember pico is 10 to the minus 12. So we have 1 times 10 to the minus 12 newtons. We have 30 times 10 to the minus 6 meters per second for a velocity, and we get a tiny, tiny little power. Okay, we get 3 times 10 to the minus 17 watts. So not a lot of power does it take, but we're talking about one individual bacterium. So not a surprise that the number will be very small. So the next part of the question then is, it says, burning one ATP molecule yields about 8 times 10 to the minus 20 joules. So a tiny little piece of energy there. And this energy can be used by the cell to do work, such as turn the motor that propels its flagella, that gives it that motive force to move forwards. So the question is, how many ATP does E. coli have to burn every second to meet the power requirements you found in A? Okay, so let's see how much ATP this will take. All right, so we know power, work per time, so that's joules per second, right? So we know joules per second. We're looking for how many ATPs per second. So all you have to do is take your joules, your 3 times 10 to the minus 17 joules, and divide by the fact that there are 8 times 10 to the minus 20 joules in each ATP, and we end up with about 375 ATPs per second, this is. Okay, so this is how many ATPs per second, okay, that they have to burn to meet your power requirements. Okay, so it is a lot of ATP. Okay, you're right. So, so that's an example of how this would apply in a biological setting. Does anybody have questions about, at least about the physics? I can't answer a lot of questions about ATP, but I can't answer the physics questions. Okay, so let's go on then and talk about the next topic. So the topic for chapter 7 is momentum, in particular what we call linear momentum. And linear momentum is basically equal to the mass of an object times its velocity. Okay, pretty straightforward. So the units will be kilogram for mass and meters per second for velocity. And this is one of the few physical quantities that doesn't have a name based on the name of an old physicist. So it's not like Newton or Joule or a watt or all of those units that have a name. This, for some reason, momentum was never named after a previous. Okay, someone wants me to go back to the last slide for a second. Okay, we can go back just for a second. There's the last slide. I know that went by kind of fast, but you do get to go look at them later as well. Is that enough time? You're welcome. Okay, so back to momentum. All right, so the reason we call it linear momentum too is because we are going to run into something called angular momentum, which will be the momentum of something that's spinning. Whereas this is the momentum of something that's translating, that's moving with some linear velocity. The most important thing to remember about linear momentum is that it's a vector quantity, okay? And we have to, just like with forces, when we add momentums, we have to add them as vectors. We have to deal with components and all of the things we learned about vectors. Power is a scalar. Yes, power is a scalar. Okay, because remember, work was a scalar, time is a scalar. Okay, and you have to be a little careful because power is also a p. So I will use little p for momentum and big P for power. Okay, which is not the case in the pre-lectures, as we'll see in a second, but I tend to try to distinguish between the two with big and small letters like that. Okay, so what did you learn about linear momentum in the pre-lecture? What you learned was, one of the things you learned, hopefully, is that when a net external force is applied to an object over time, its momentum will change. That's probably not a huge surprise, because we know when you have an external force applied, you will have a change in velocity, and momentum depends on velocity, right? So it's probably not a surprise that momentum will change when you apply a force, right? You're going to have an acceleration. All right, so this is how you might write that expression. So here is the net external force, so the sum of the external forces. You multiply that by the time elapsed, how long the force is being applied, and that will tell you the change in momentum of the object, which we can write as the final momentum vector minus the initial momentum vector. Okay, that's how we always write our changes, right? Final minus initial. Right, and momentum is not on the next test. It'll be on the one afterwards. It's not on test 2. Okay, so here's a nice example of a force being applied to an object over time to change its momentum. This is exactly what happens when you hit a baseball with a bat. So here's a little sort of schematic, okay, of a ball, a baseball, incoming with an initial velocity v0x. We're going to look at everything in along a horizontal direction here. And usually, even though there's likely other forces like gravity acting for just the time of the collision, okay, because especially in a case like this with a baseball hitting a bat, the collision is so fast, okay, that it's really going to be, and the collision force is so large that we're going to ignore things like gravity and air resistance here and just look at the force that causes the major change in momentum, the impact force of the bat on the ball. Okay, so here's our force. So, right, when the ball hits the bat, right, there's going to be a force, okay, pushing it to the right if the ball comes in heading towards the left like that, and that's going to make the ball turn around. And in this case, not only does it change direction, it also increases its speed, so it ends up with a final velocity of Vx, points in the opposite direction. So how can we calculate change in momentum? So now we're just looking at x components, because we only have a force in the x direction, so that's only going to impact the x direction, the x component of the momentum. So we're going to have the final x component minus the initial x component of the momentum. And so what do we have? We have mass times the final x velocity minus the initial x velocity, like that. Okay, and so that's how you would calculate the change in the x component of the momentum here. Okay, you just take the Vx, the x component of the final velocity, minus the x component of that initial velocity there. One thing to be careful with here, with problems like this, is signs. Okay, because remember, Vx and V0x are components, so they can be positive or negative. So you want to be careful with the signs. For example, in this case, Vx is positive, but V0x would be negative, right? If you define the to the right direction to be positive. Okay, and that's going to make a difference to what your delta P looks like. Okay, so I thought we would do a question on this one. So here's our first poll question. So let's start the poll going. We only got 3 choices here. This is an easy one to set up. Okay, so there's our poll. So what's our question? Our question is, so you have 2 same mass balls moving at the same speed. So they both have V0x before. Notice I have a before scenario, and then I have 2 after scenarios. Okay, because with these problems, you want to have before and after. Okay, before the collision, after the collision. Okay, they both undergo a collision with a wall. One bounces back at the same speed it came in at, and the other comes to rest immediately after the collision. Which ball exerts a larger average force on the wall during the collision? So remember, the ball is exerting a force on the wall, and the wall is therefore exerting a force back on the ball, and it's that force of the wall on the ball that's changing the ball's momentum. And we know that the change in momentum is equal to the external force applied. Okay, I think maybe we'll do like 10 more seconds. All right, 5, 4, 3, 2, 1. Let's see what everybody thinks. Okay, so what do we got? We have, there's a reasonably big consensus. The biggest group is voting for A, that the ball that bounced back exerts a larger average force on the wall. But we also have a reasonable group for B and C. So let's have a look and see how you would figure this out. Okay, so the first thing to realize is that we said that ball 1 bounces back at the same speed it came in at. So that means that the final velocity Vx would just be equal to minus V0x, right? Okay, it's the same magnitude in the x direction, just opposite direction. Okay, so then if we go and calculate the change in the x component of the momentum of ball 1, which is, remember, we just saw this, it's Vx minus V0x, and we plug in minus V0x for the final velocity, we get that the change in momentum is minus 2m V0x. Okay, it's a negative change because the object goes from going in the positive direction to going in the negative direction. Okay, and it's minus 2 times basically the initial momentum of the ball. Now if we look at object 2, what happens? So same formula, looking at the change in the x component, but now our final velocity is 0, and what do we get? We get that the change in the momentum, change in the x component of the momentum is just minus mv0x. So it's just minus the incoming momentum because it went from that incoming momentum to no momentum. Okay, and like I said, the change in momentum is proportional to the force, right? Because the change in momentum is the external force, in this case, the force of the wall on the ball times the time. So therefore, because the basically when the ball bounces back at the same speed, you get twice the change in momentum you would if the ball just stopped dead. So that means twice the force would have to be exerted if the collision had the same time. And so that means the ball that bounced back, okay, because in this case, we said they have the same impact time, so that meant that delta t was the same in each case. Okay, so it's the ball that bounced back, all right, that basically exerts a larger force on the wall. And this is something you actually see in real life. For example, if you've ever compared like hail to rain, falling hail to falling rain. Falling hail, if it's big enough, can do quite a bit of damage to, say, car windows and so forth, whereas falling rain, which is essentially like something where it essentially comes to rest when it hits because the water spreads out, doesn't typically do damage when it hits the car. Good. Okay, well done on that one. So let's move on now and talk about a system. So instead of an individual object, you can also talk about the momentum of a system. So if you have a collection of moving objects, then, so say you've got these 3 objects and they're moving in different directions, they have different masses, and you want to know the total momentum, it's just a vector sum of the individual momentums, or momenta, if you want to say it in Latin. So it's just a sum of each individual, so it would be like m1 v1 plus m2 v2 and so forth. So if you have a system, now we can talk about looking at a net external force applied to a system. Okay, so where you choose a certain number of objects to be in your system, and then you don't look at the forces between those objects. Okay, you don't look at the forces the objects exert on each other, you only look at the external force on the system, and if that force is 0, then you can say that the total momentum of the system is conserved. So this is a lot like our energy conservation, where basically that means that the quantity doesn't change over time. So, and we can see that pretty easily here with our formula from before. So if the net external force times the time elapsed equals the change in the total momentum of the system, and if that's 0, that means the change in the total momentum is 0, and that means that basically the final total momentum of the system must be equal to the initial total momentum of the system. Okay, that's a quantity that's going to remain the same. Okay, it's a conserved quantity. Now in the pre-lecture, they call this the law, which is the correct name. It's the law of conservation of momentum. Okay. But the thing I just wanted to point out is in the pre-lectures, they like to use capital P for total momentum. And I don't like that because I like to use capital P for power. So therefore, and I'm not going to write capital P. I'm going to write little p with a total next to it to represent momentum. So you know exactly which momentum we're talking about. Okay, so this is our law of conservation of momentum, and it's an incredibly powerful law, just like our law of conservation of energy. Okay, the energy cannot be created or destroyed, just transferred, moved around. It's a similar situation with momentum. This is another one of the big fundamental conservation laws of physics. Physicists like conservation laws, you'll see, because they help us understand systems and how they change over time, and which things stay the same and which things don't. Okay, so we have another poll question about, and this one is about momentum and about kinetic energy, which we've run into already. So let's get this set up. Okay, so there's our poll. So the question is, so you have a system of particles and it's known to have a total momentum of 0. What can you say about the total kinetic energy of the system? So your choices are, you can say the total kinetic energy is also 0, the total kinetic energy is greater than 0, the total kinetic energy is less than 0, or you can't say anything about the total kinetic energy. All right, one thing to think about here is what does it mean to have a total momentum of 0? So this is the total momentum of the system of particles. All right. So looking at the responses so far, it looks like this one is kind of confusing to people. So I'm thinking maybe we should go into breakout groups. What do you guys think? And have a talk about this, about what it means for total momentum to be 0. Because I'll tell you right now that about 2/3 of the class have gotten this wrong. Yes. So what I think I'm going to do is, just for fun, I'm going to give you 2 minutes to go into breakout rooms. Okay, or say 3 minutes. So we'll give this a try and see if it works. Okay, because I haven't tried this before with you guys. If you get disconnected, so let's see. So you're going to be in groups of about 7 or 8 people. If you get disconnected, just reconnect yourself again. Okay, so we're going to do, yeah, so that should work. All right, here we go. So we're going to go into breakout groups right now. 1, 2, 3. Okay, we're going to end the breakout groups now. Ending the breakout groups now. Sorry about that.
You try it, well, you can hardly try it. Well, yeah, I think you can be quite successful. You make a nice appearance, except you don't say yeah in court. You say yes, Your Honor, no, Your Honor. Right?
Just got to turn your mics off now. Okay, so back out.
So let me hear your argument before the court. Say, Your Honor, I wish to present the following evidence of my defense. You need to say that. Your Honor, I wish to present the following evidence of
my
defense.
All right, somebody's got something with their TV running, so you got to turn it off.
Okay. I've got the ticket here that says.
All right, I think I muted whoever it was. Somebody's watching TV. All right, so we're going to try this one again. And hopefully, oh, someone else has got their mic on. So this is the problem with people turning the mics on. All right, we're going to try this one again and see what you guys found out in your discussion. All right, I'm going to go and mute everybody again. So it was good to see lots of chatting in the groups. Okay, I think we'll do 10 more seconds on this. Go ahead and guess if you're not sure. All right, 5, 4, 3, 2, 1. All right, so we are still somewhat undecided. The answers definitely changed before before you guys went and chatted. Lots of people thought it was A, and now we seem to have an equally split indecision between A and B, which is interesting, and then a few C's and a few D's. And it turns out actually indecision between A and B is sort of right, because the answer is actually D, that you can't actually say anything about the kinetic energy. Why is that? Well, so remember, momentum is a vector. So the fact that total momentum equals 0 does not mean the particles are at rest, does not necessarily mean they are at rest. They could all be at rest, okay? Or they could all be moving such that their momenta cancel each other out when you add up all the vectors. So in that case, so they could either all be moving and have their momentums canceling out, and then your kinetic energy would be positive, or they could all be at rest, and then your kinetic energy could be 0. Okay? So, so the answer is you really can't say. Okay? You can't say whether it's positive or 0. The only thing you can say, I mean, it's not totally so that you can't say. We do know that it's not negative. Okay? So, because kinetic energy will never be not negative. All right? So, sorry about that. Okay? But that's just to keep in your mind the difference between scalar quantities and vectors. And the vectors you can have all these quite big momentums, but they can still cancel each other out. All right. So for the rest of the time, we're going to talk about collisions, which is also most of the topic for next when we get back after the break. So imagine you have two objects colliding, object 1 and object 2. So this is a system, okay? And so you've got object 1 with velocity 1 and initial. This is before the collision, and object 2 with v2 initial before the collision. And here they are colliding, okay? So they collide with each other, and then afterwards, Object 1 will have a velocity v1 final, and object 2 will have a velocity v2 final. So in this case, they both bounce back, okay? So then the question is, they're both bouncing back, but it could be that they both go to the right or they both go to the left. We don't actually know because it depends on the nature of the collision. And we're going to see next time that there are collisions where things stick together and stay together. There are things where they bounce back, but there's still some energy loss. And there are cases where they bounce back perfectly and there is no energy loss. Okay. So you want to keep that in mind, that there are different kinds of collisions with different things that can happen, but no matter what happens in terms of energy in a collision, momentum will always be conserved, okay, provided there's no net external force, okay, and we will only be looking at collisions where there's no net external force. All right, so there's no friction here. We're not worrying about air resistance. Okay, we are not worrying if the objects are, say, rolling on a surface, and so any gravity would be balanced out by a normal force. Okay, so in that case, then the total final momentum will equal the total initial momentum. And so it would look something like this. You'd get a vector sum, you'd add up m1 times v1 final plus m2 times v2 final, and so forth is equal to, if you had more objects, then you'd have a 3 and a 4. We're pretty much only going to do collisions with 2 objects, okay? And so it would look something like this. And so what I thought we would do now is there's a really nice simulation called the collision carts simulation, which we're going to have a look at now. So I'm going to go try and find it. Here it is. So this is called the collision carts simulation, and it's kind of a fun simulation because you can play around with the initial velocities of the 2 objects. You can play around with the initial masses of the 2 objects, okay? And you can also try out different collisions. So like if we start right now and look at this scenario, we have 2 1-kilogram objects, and they're both traveling with the same speed, but in opposite directions. So same mass, same speed, opposite directions. What does that tell you about the initial total momentum? What would that be equal to here? 0. Good, yes. So this starts with 0 momentum. And if we watch what happens, they collide and they bounce back with equal and opposite velocities, okay, in what we call a perfectly elastic collision, okay? So I've reset that. So we can also look at, so like I said, we can play around with changing the masses here, okay? And we can also change around with playing with the velocities, okay? So we could, let's actually, before we do that, let's play around with the type of collision. Okay, yeah, we can do it. We'll do an explosion. So let's do an inelastic collision. So this is the kind where they stick together. So here they come in and they stick. Kind of boring, okay, because they were both going the same velocity, okay? And so total momentum before was 0, total momentum afterwards is 0, so they both kind of just come to rest, okay? We can try that again for inelastic, but now say we make one of them go faster, like that. Say we make mass 1 go faster, and we do it again. Now they travel off towards the right, okay? So it's kind of fun to play around. So yes, we can also do an explosion. So there's our 2 objects. Okay, so an explosion is sort of a reverse collision, right? So this is sort of the opposite of the one we just saw, okay? But now they both start with 0 velocity and countdown, boom. And they go flying off. We started with 0 momentum to start with. We end up with 0 total momentum at the end because they're going in opposite directions, but with the same speed and the same mass. Okay, so now we can go back to this scenario here, okay, where we're at, we're doing an elastic collision, and I just wanted to double check which one I was going to do here. Okay, So let's, for example, increase the mass now. So say we increase the mass of the one on the left, and we start. So now the one on the mass has more mass, which means it has more momentum. Oh, but I have to give them initial velocities. That's not good. Okay, I lost my initial velocities. Here we go. So that one has 5. This one has -5. Okay, and we start. Oh, that was -4. Okay, and so you can see that they both bounced back there. Let me try that again. I wanted this one to be -5. But you can see the one with more mass bounces back a little bit, and the one with less mass bounces back a lot. Okay, and then if we increase the first one's mass, I have to reset everything here. They're both 5. If I increase this one's mass to 3 kilograms, and I started going, then you get an interesting result. In that case, okay, where the initial one is 3 kilograms and the one on the right, the blue one, is 1 kilogram, this one comes to rest, the red one comes to rest, and the blue one goes flying off to the right with a velocity of 10 meters per second. So I thought we would have a look at that one. So if we get rid of that for a second, we go back to our slides really quick. Okay, so this is the scenario we were just looking at. Okay, our before was two carts, 3 kilogram, 1 kilogram, okay, with equal and opposite velocities. And afterwards, we saw that the 3 kilogram one came to rest, and the 1 kilogram one went off at 10 meters per second. So we can actually do the math here and see if that makes sense. So we have our momentum before and after, set them equal to each other. We're going to put in all our numbers. So we have our 3 kilograms times 5 meters per second plus 1 kilogram times -5. And we're going to compare that to the, oh, you know what? I flipped my final and my initial here. I apologize. I just realized. I'll fix that. Okay, so actually the stuff on the left is the initial and the stuff on the right is the final there. So I'll have to flip-flop that. Okay, so but either way, you can see that both sides have the same total momentum. Okay, so they both have 10 kilogram meter per second on either side. So that's how our conservation of momentum works in one dimension. There was an example in the pre-lecture in 2 dimensions, but I don't think we're going to do any problems in 2 dimensions in this class. We'll pretty much stick to one-dimensional collisions because that's complicated enough for what we're going to be doing. All right, so I think we're going to stop there. Okay, and we'll do some more collisions and momentum and fun stuff like this when we get back. So have a good reading break. I hope you all are able to find some time to relax. There will be one more sapling homework due right after break, due on the Tuesday. That'll only be the rest of the energy stuff. I'll hold off on the momentum until after the test. Okay, all right. So we'll stop there, and I will stop recording.